Okay, welcome back. Today we're going to discuss electron configurations, just a reminder of how to write an electron configuration and what they mean. Remember that last year we used our periodic table of elements to guide us through the way the electrons fill their energy levels. We used periods to represent the energy levels. We used the partitions on the periodic table to represent the sublevels. We put electron number 2 over there. And then we used each box to represent an electron. So if you remember, this is what an electron configuration looks like. This electron configuration has a total of, let's see, 6, 7, 8, 9, 10, 12, 9, 10, it's 22, 25 electrons. And that would represent either an atom of manganese or it could be an ion of something else, anything containing 25 electrons. Remember that we learned how to write shorthand, so if we are writing the shorthand for an element like manganese, we're going to use the electron configuration for argon. So we're going to say, hey, all of the electrons that argon has, plus these extras, which would be the 4s2, 3d3. The nice thing about the shorthand configuration is that it's very easy to see the valence electrons. Now we use the noble gases because those are elements that do not ever gain or lose electrons. We know that all of the other elements on the periodic table have the option of gaining or losing electrons, but the noble gases do not. Remember that when we do orbital diagrams, that's just an extended version of the electron configuration where we'd have our 4s energy level and sublevel, and then we know since S sublevels all have one orbital, this horizontal line represents the orbital, and in that orbital we'll put 2 electrons. The electrons are drawn as arrows, and they are opposite in direction due to the electron spin. We know that the 3d sublevel has 5 orbitals, so we need to draw 5 horizontal lines. And in there we're going to put 3 electrons. And remember that you put 1 electron in every orbital before you go back and pair them. So that's a quick little review on electron configurations and orbital diagrams. The numbers are the principal quantum number, so the 1, 2, 2, 2, 3. Those tell us the energy level of the electrons. The S, P, D, and F tell us the sublevel, which is the shape of the electron cloud. And those superscripts, 2, 2, 2, 6, 2, those are the actual electrons in the orbitals. Okay, so there are some special cases with electron configurations. There are some scenarios where there's just a little bit more stability than what we actually write. It seems that the electrons are a little bit more likely to stay in their orbital if the orbitals are either half-filled or whole-filled. So we can see for this example with copper, this ends in 4s2 3d9. That's how we would normally write the electron configuration, which is not the correct electron configuration. Because what actually happens is one of the electrons from the 4s jumps over here to the 3d. So the true electron configuration is 4s1, 3d10. And that is a much more stable electron configuration than having the neither half or whole filled 3d sublevel. So in the transition metals is really where this occurs, where we have, if we have a scenario where an electron can move from the 4s, making it half filled, to the 3d, making it completely full, then that's going to do that rather than keeping the 4s full and the 3d9 neither half or whole filled. Okay, and if you look at your periodic table, it makes sense where else this might occur. Consider where the D sublevel would be almost half filled. The D sublevel is half filled at 5 electrons, starting at scandium 1, 2, 3, 4, 5. Right, so the chromium group ends in D4. So if you look at chromium's family, chromium tends to have, or chromium's family, that whole family tends to end in or something S2 is how we would normally write it, and then it would be D4. But by moving one electron over, we end up with S1, D5. So here we started with the S sublevel, which was full, and the D sublevel, which was neither half or whole filled. But by moving that electron over, now we have two orbitals that are both half filled, and that is more stable than having an electron, an orbital that's whole filled and one that is neither half or whole filled. The reason this happens in transition metals is because the energy difference between the S sublevel and the D sublevel is minimal. It's so small that you'll see in some textbooks that they say that the transition metals valence electrons would include whatever is in the S sublevel and also what is in the D sublevel. Those are just different schools of thought. Some people include them, some people don't. I tend to include them because the energy level is really, really small. The energy difference, I'm sorry, is really, really small. And we know that electrons freely move throughout the D sublevel and the S sublevel that come before it, and this is why we have these beautiful colors that are exhibited with the transition metals. So I tend to say that copper has, instead of 2 valence electrons, it has 11. But really that's just the school of thought. The energy difference there is just really, really small. Okay, a little reminder about electromagnetic radiation. We studied last year waves. We know that wavelength is measured by or indicated by the Greek symbol lambda. That is our variable that we use for wavelength, measured in nanometers, 10 to the negative 9 meters. Frequency, it's really the Greek letter nu, but I can't seem to find that on the presentation, so we'll use that. It's the reciprocal of a second, also called a hertz. And of course the speed of light. And we know that wavelength and frequency are inversely proportional. You can see this from the equation, right? In a straight line, its speed of light is equal to wavelength times frequency. But if we put the wavelength and frequency on the other side of the equal sign, we can see that as frequency increases, wavelength decreases. So the faster the wave is going, the shorter the wave is going to be. Remember that we measure wavelength from two similar points on the wave. Here I've drawn it from crest to crest. Doesn't have to be that though. It could be trough to trough. Does not matter. We learned last year that Planck kind of started the ball moving on quantum theory, and he studied hot glowing gases, and he determined that he could calculate the amount of energy that was given off, or the amount of the frequency of the light that was given off based on the amount of energy that was put on. And by the way, you guys, this is energy per photon. So this is for one photon. If you were going to get a mole of photons, of course, you would have to multiply that by Avogadro's very famous number. And then, of course, Einstein with his theory of relativity saying that energy is equal to mass times the speed of light squared. So mass and energy are directly related if they're going extremely fast. And then we had de Broglie, who put those things together. And he said, hey, if E is equal to mc and E is equal to hv, well, how come mc isn't equal to hv? And they are. And then he replaced a couple of things. Instead of using specifically the speed of light, he used velocity of the particle. And instead of using frequency, he used what frequency is. Speed of light divided by wavelength. So if we rearrange this, so before we take out the c, mc is equal to hc over lambda. So the c's will cancel out if we solve for lambda. Lambda mc equals hc. Lambda m equals hc over, over c. Let's just get rid of that and just do that too. You can see that the speed of light cancels out. So there's de Broglie's equation, that we can calculate the wavelength if we know the mass and the velocity of the particle, and using Planck's constant. If you remember, Planck's constant is 6.626 times 10 to the negative 34 joule seconds. That is not a number you have to memorize. Speed of light, I would think, is something you should know just for your own educational purposes. Okay, and then Bohr came along with his model, and he was studying the spectrums for the emission spectrums for glowing gases. Planck looked at glowing solids. And we know this, that white light is a continuous spectrum where all the beautiful colors of the rainbow come together, Roy G. Biv, right? And there's no break in between any of the colors. The colors blend one from the other. However, in a bright line spectrum, these are specific wavelengths that are showing up if we're going to bend that light. Only some wavelengths are present, not all of the wavelengths are. And we can calculate the energy of that using the previous equations. If you remember Bohr's model, these are some bright line spectrums down here. This is a continuous spectrum. Remember that Bohr said that anywhere we see a wavelength of light, that represents an electron transitioning from one energy level to another. And you can see from this diagram over here that the amount of energy that it takes for an electron to transition changes as the electron moves farther away from its own nucleus. So the amount of energy needed to take an electron away from energy level 1, that's a lot of energy. So when it comes back to its ground state from its excited state, it's going to release a lot of energy. So we're talking about high energy waves here, small wavelengths here, right? Blue lights rather than red lights. But you can see, to remove an electron even one energy level, but that's farther away, if we're moving only from energy level 7 to energy level 6, that's a teeny tiny amount of energy. It's probably not even in the visible light spectrum. It's probably not something we can see. So the farther the electron is from its own nucleus, and it takes less energy to transfer between energy levels, and therefore less energy is given off. Bohr's model was a mathematical model, and it was a great model. It worked wonderful for hydrogen, but it did not work for everything else. So the hydrogen, he said, the electrons in the atom moved around in an orbit. And here's his mathematics. He says the energy required for an electron to transition from one energy level to another is equal to negative RH times Z squared. Z is the atomic number, if you remember your AZ format. So in this case, because we're only dealing with hydrogen, that's always going to be 1 squared. And then N squared would represent the energy level. And his mathematics were great for hydrogen, but they kind of fell apart when we got to more than 1 electrons. It's a good start. So I would expect you to do some calculations using Bohr's model of the atom and be able to calculate differences from one wavelength, from energy changes from one to another. So it says calculate the change in energy of an electron that moves from 5 to 1. So we know that the change in energy, if it's moving from 5 to 1, that energy is going to be released. So keep in mind that that's going to be a negative number. So we're going to do, using Bohr's model, negative R, which is 2.178 times 10 to the negative 18 joules, times, for the final minus initial, the final is 1 squared, which we know is 1, over 1. That's the energy level. So this would be the energy final minus the energy initial, which is going to be negative 2.178 times 10 to the negative 18 joules, I'm running out of space, times 5 squared, times 1 squared, that's the atomic number for hydrogen, over 5. And when you calculate that, you will see that you have a negative number, and that is the amount of energy that is needed to, or that is given off when that electron moves. I'm going to pause this and do this calculation just really, really quick. Okay, so in doing this, I see that the energy is negative 1.74 times 10 to the negative 18 joules. And from that, we can calculate the wavelength of the light using our other equations. We know that E is equal to hc divided by lambda. That's de Broglie's equation. So if we want to know the wavelength is equal to hc divided by E. That would be Planck's constant times the speed of light divided by the energy change. So the wavelength is equal to 6.626 times 10 to the negative 34 joule seconds times the speed of light, 3.00 times 10 to the, I'm going to erase this. All right, back to it. Wavelength is equal to Planck's constant, 6.626 times 10 to the negative 34 joule seconds times the speed of light, 3.00 times 10 to the 8th meters per second, divided by the energy, in this case, 1.74 times 10 to the negative 18 joules. Now listen, remember that the negative just tells us the direction of the energy. There is no such thing as a value of energy that is less than 0. So calculating this, we're getting a wavelength of 1.14 times 10 to the negative 7. And look at our units. Joules cancel, seconds cancel. The unit is meters. And then we might want to convert that into nanometers at some point. Okay? Now moving on to the modern model of the atom, which is the quantum mechanical model. Schrödinger is the father of the modern model of the atom. And instead of treating the electrons as particles moving in orbits, he treated them as a wave. And he was able to calculate a probability distribution for where the electrons lie. Now Schrödinger's model for the atom is also mathematical. We're not going to get into the large mathematics of it, but we will talk about quantum numbers in the next video. Quantum numbers are the basis for an electron configuration. There are 4 quantum numbers, and we can use those numbers to kind of guide us through what the electron configurations are. You know, there are certain quantum numbers associated with each energy level, sublevel, and orbital within that sublevel. So next time, quantum numbers and how that relates to electron configurations. Thank you.